Today we're going to talk about even or odd functions, and most functions are actually neither. They're not even or odd, and um, you're not really going to see the application of why even and odd functions are important. Um, do you want me to start with the actual definition that's harder to understand? Or, well, you have to get both, or do you want to see the easy definition? You want the easy one first? Hard then easy? Okay. So, even functions. Not many functions are even. Okay? An even function is any function where f of negative x is equal to f of x. What does that mean? F of negative x is equal to f of x. Okay, good. That is a perfect way to describe it. So f of negative 2 gives me the exact same number as f of 2. Okay? And f of 3 gives me the exact same answer as f of negative 3. Okay? So graphically, what would that look like? Can you guys visualize that? Whenever I plug in a number or its opposite, its additive opposite, I get the exact same answer. Can you think of a shape that does that? A circle would, but it's not a function. Okay? So the fact that it says f of negative x means it's a function. So a circle doesn't work because the circle's not a function, but maybe the top half of a circle or the bottom half of a circle or a parabola. So let's look at y equals x squared minus 4. Okay? Let's plug in 1. What is f of 1? Negative 3. Okay? Let's plug in f of negative 1. I get negative 3. That's a good sign, right? Okay, let's plug in 6. Or how about negative 6? What happens when I plug in negative 6? 32. And if I plug in f of 6, I also get 32. Is that proof that this is an even function? No. I only need to find one case when it's not true to prove that it's not even. So the only way to prove that this is true using this method would be to plug in every single point. And that's gonna, we'd have to break for lunch. Okay? So just showing that some examples work is not enough to determine that a particular function is even. We have to test every number. And instead of doing it individually like I was there, let's just go back to the original definition. Let's plug this in. Okay? So f of negative x is negative x squared minus 4. So, what do you notice about the quantity negative x squared minus 4? What happens when I square negative x? It turns into positive x squared. Right? And what do you notice about this? That is the original function. Does that make sense? Right. So the definition of an even function is if you plug in negative x and simplify, your result is exactly the same as the original function. Okay? That is the difficult definition. So are all quadratics even functions? No. Okay, let's use a different quadratic. Let's do x squared minus 3x minus 5. Okay, let's plug in, give me a number, 3. So 3 squared is 9, minus 3 times 3, 9. So 9 minus 9 is 0. 0 minus 5 is negative 5. Now let's try negative 3. Okay, negative 3 squared is 9. Negative 3 times negative 3 is 9. 9 plus 9 is 18. 18 minus 5 is 13. What do you notice? That point didn't work. Do I need to test any more points? No. Okay. This one is not even. No. And it's kind of like saying, think of every number on the number line. Okay. Usually when we say think of a number, we mean think of a natural number, right? 1, 2, 3, 4, 5, 6. But really, if you said think of any number, most of them are going to be decimals, right? So if you look at the entire number line, you have a couple that are even and a couple that are odd, but most of them are none of the above, right? And the same is true of functions. Most functions are not even or odd. They're just none of the above. So when you determine that a function is not even, you cannot say it's odd or even not odd. You actually have to test it. So this is kind of a slow way to determine if something is even or odd. And you can't prove that something's even or odd this way, or sorry, even. You can disprove it. So let's go back to what we did here. F of negative x. What would that look like? Well, parenthesis negative x squared minus 3 times negative x minus 5. Well, what happens here? The squared kills the negative. Okay, and I get x squared. What happens here? I get plus 3x minus 5. And what do you notice? This equation and this equation are not the same, which means it's not even. Does that make sense? You guys seem to pick up on this really well. Maybe I'm a better teacher than I've been before, because this is usually kind of complicated. So that's even. What about an odd function? An odd function fits this definition. F of negative x is equal to negative f of x. And that's a little bit harder to understand. Can anybody figure out what that means? Maybe. What do you mean? What does f of negative x mean? So let's write one out. F of negative 2 is equal to negative f of 2. Does that make more sense? So plugging in negative 2 will give me the same answer as what? Good. So this says plugging in negative 2 will give me the same answer as the opposite of plugging in positive 2. Okay? Does that make sense? So let's do Let's just do a couple and see what happens. Okay, f of 3. So I plug in 3. 3 squared is 27, minus 9 is 18. Okay, and that should be exactly the same as what? So f of 3 should equal the same thing as the opposite of f of negative 3. So let's plug in negative 3. Negative 3 to the third is 27, and 27, negative 27, thank you. So negative 27 plus 9 is negative 18. So if I plug in negative 3, I get out 18. And then this negative in front changes that 18 to a negative 18. So when I plug in 3, I will get the opposite number than when I plug in negative 3. Okay? All right, so what about f of negative 1? What do I get when I plug in f of negative 1? Well, negative 1 to the third is negative 1, plus 3 is 2. Okay, when I plug in f of negative 1, or sorry, positive 1, 1 to the third is 1, minus 3 is negative 2. Did it work? Did plugging in negative 1 and positive 1 give me opposite answers? Right, so I'm trying to display it two different ways. But basically it's saying when I plug in any number and its opposite, I should get opposite answers. Or you can say the opposite answer is the same as the original answer. The opposite of the opposite answer. Okay? Does that make sense? All right. Well, once again, just showing that something works a couple times is not enough to guarantee that it works forever. So we have to plug in negative x. So f of negative x. What would that look like? So it's negative x, parenthesis, to the third, minus 3 times negative x. What is negative x times negative x times negative x? Negative x to the third. And then negative 3 times negative x is plus 3x. What do you notice about this? It's the exact opposite of the original, which means it's odd. Right. If the result here is the exact opposite of here, that is an odd function. Yes? So if we, so if we plug any number and its opposite into the equation, then the answers will also be opposites. Well, yeah, if that's the way you want to think of it, it should be okay. All right, now here's the easy definition. Okay, even functions are symmetric across the y-axis, meaning every single even function has a left side that is exactly the same as the right side. So this would be an even function. Okay? This would be an even function. Or we talked about maybe the top half of a circle, as long as it's positioned in the right place, would be an even function. So are all quadratics even functions? No, just the ones that are symmetric across the y-axis. Okay? Odd functions. And this is a little bit harder. Odd functions are symmetric across the origin. And you've probably never talked about point symmetry. And it's a little bit confusing, but it's something we do in mathematics quite a bit. What that means is, let me give you an example. This is symmetric across the origin. So instead of reflecting across a line, we're going to reflect across a point. So you pick any point on the graph right here, and you draw a line to the origin. And then you continue that line so that it's the same length as the original line. So this and this are the same size. And then you can do that with every single point. See that? This point goes right there. This point goes right there. And that is symmetric across the origin. Now, in order to be symmetric across the origin, there's only one place you can hit the y-axis. That would be at 0. Does it mean it has to hit 0, 0? No, because here's another one that's symmetric across the origin, right? Yeah, if it hits the y-axis, it has to hit at 0. But a lot of them don't hit the y-axis at all. Okay? All right. What about polynomials? How do you tell if a polynomial is even or odd? So let's say I had 2x to the 4th minus 6x squared plus 2. Let's plug in negative x. F of negative x. 2 times negative x to the 4th minus 6 times negative x squared plus 2. What is negative x to the 4th? What is negative x times negative x times negative x times negative x? X to the 4th. That 4 kills the negative, and I get 2x to the 4th minus, it's not plus, because this square kills that negative. What do you notice about that function? It's identical to the original. So that means it's even. Okay. Is this odd? Well, we would just use the same thing, right? Plug in negative x. Nope. Plugging in x wouldn't do anything. You plug in negative x and see if you get the opposite answer. And you can't be even and odd at the same time. So no. Okay. What about this one? Let's plug in, actually, let's do this. Let's plug in negative x. 2 times negative x to the 5th minus 6x negative x to the 3rd minus negative x squared. What happens with this first x? It stays a negative. So negative 2x to the 5th. What about the next one? It turns into a positive. And the next one stays negative. And how does this equation compare to the original? It's not the exact opposite. So is this even? Nope. Is it odd? No. Now, which piece made it not odd? The x squared. So if I went in and changed this x squared to just an x, then this turns into a plus, and it is odd. And what do you notice about odd functions? Or sorry, look up here, get rid of this. And even polynomials. The exponents are all odd or even. Okay? So if you have nothing but even exponents, and by the way, this one is x to the 0, which we're going to count as an even number. 4, 2, 0, even function. Down here, 5, 3, 1, even or odd function. If you have some combination of odd and even exponents, it's neither. Okay? What about absolute values? Is that even or odd? Well, graphically, it looks like this. So let's think about it. F of negative x. Is there any difference between the absolute value of x and the absolute value of negative x? No. This is the absolute value of x. Okay? Now what about this? So let's do g of x equals the absolute value of x plus 1. Okay, so I need to plug in negative x. And let's try some numbers. Let's try, for instance, 1. 1 plus 1 is 2. So g of 1 is 2. If I plug in 1 here, negative 1 plus 1 is 0, and the absolute value of 0 is 0. Is that even? No. And actually, that graph has been shifted to the left 1 unit. How do you go up with it? It's on the outside. So h of x equals the absolute value of x plus 1. Is that even? Yes. Because you plug in negative x, and these are exactly the same. So if an absolute value has an addition or subtraction inside, it's not even. And if it has an addition or subtraction on the outside, it is even. And multiplication's not gonna matter in these. All right, let's see if I have covered everything. Like which one? So let's do 16. So h of x is equal to 1 over x minus 2x. So I need to plug in negative x and see if that changes anything. So h of negative x, 1 over negative x minus 2 times negative x. Is there another way to write this that makes a little bit more sense to us? Either put the negative on top or out front. We usually don't like the negatives on the bottom. So whether you do negative 1 over x or negative 1 over x, it's the same thing. Okay, so negative 1 over x, and this one turns into plus 2x. And how does this compare to that? It's the exact opposite, which means it's odd. Yep. And that's how you work these. You plug in negative x, and then you see, do you get the original equation, or do you get the opposite of the original equation, or none of the above? Okay, and then 17 through 27, you're going to state the domain. So let's look at 18. What is the domain of 18? What are the x values? Nope, negative 4. Right? The furthest left that graph gets is negative 4. Right? How far to the right does it go? To infinity. So the domain for 18, here, yes, thank you. So let's take a picture of this. Make sure everybody remembers how to do these. Right there. Okay, so the domain is from here over. Those are the x's that belong to the graph. So the domain is going to be from -4 to infinity. Is -4 part of the domain? Yes. How do I know? Because this is a closed circle. So -4 gets a bracket, and infinity gets a parenthesis. Okay, what about the range? The range is from here that way, but we always list the small number first. 3 is the biggest number. -infinity. So from -infinity up to 3. Does 3 count? Yes. So parenthesis, bracket. Okay, then it asks for x intervals for when from when the function is increasing, decreasing, or constant. So when is the graph increasing? When is it going up? Which x values? Well, how many pieces of this graph are going up? Just that piece right there. What are the x intervals for that? 1 to 2. It's this little piece here. Now, this is kind of outside the realm of this class. Do we include 1? And do we include 2? And the answer is, it depends on how you look at it. So in this case, we're just going to, it doesn't matter. You can either do brackets or parentheses. I'm not sure what the back of the book does. My guess is it has parentheses. So 1 to 2. How many places on the graph do we have a section that is decreasing? 2. We have this piece, and we have this piece. So what are the x values for that first piece? -3 to 0. -3 to 0. Union with 2 to, we're looking at the x's, so from 2 to positive infinity. Okay, we're looking at the x's. The only time you look at the y's is when you're doing range. So from 2 to infinity. Okay, and then are there any pieces of the graph where it is constant? Yes. This piece and this piece. So the first one would be from -4 to -3, union with 0 to +1. And again, on those increasing and decreasing intervals, well, actually, this one right here should be a bracket. This one should be a bracket. Does that make sense? And then the other ones, you could make a valid argument for brackets or parentheses. Okay, think you can handle that? All right, get to work.